So these things we have. Okay, so now let's start the proof. As E belongs to RA intersection LB and F belongs to LA intersection RB. We have ARE and ALF, and by proposition 2.3.3 we know that E is the left identity for R, E and F is right idempotent for LA, isn't it? LF you can say, LA you can say. So what we have? We have EA is equal to A, and because E is left identity for RE, and FA is equal to E. We have this. No, sorry. It's right identity. F is right identity for LF. ARE implies there exists X belongs to S1 such that A is equal to EX, correct? This we also have. AX is equal to E. Now suppose let A star is equal to FXE. Now we will show that A star is the inverse of A. So we calculate A star A. It will be A FXE into A. Now what is AF and what is EA? AF is what? A. And EA is what? A. So it will be AXA. AXA is what? EA, and EA is what? A. AX is what? E, and EA is what? A. So in this way we have proved this. Now calculate A star A star. So it is what? FXE A into FXE. Now what is EAF? What is EAF? EA is what? A, and AF is what? A. So in the place of EF what will come? FXA XE, correct? And what is AX? AX is what? E into E. So FXE, that is A star. So in this way we have proved it implies that A star is inverse of A. So we have proved that A star is inverse of A. Now we show that A star is lies in HB. Basically A star, we have proved that A star is the inverse of A, correct? Now we calculate A star. Calculate A star, that is AFXE. And what is AF? This is A X E, and what is AX? AX is what? E into E, that is E. So we have proved A star is equal to E. Now similarly we can show that now what we have ALF, we have this thing, correct? It implies that there exists Y belonging to S1 such that YA is equal to F, correct? Now calculate A star A, that is FXE into A. And what is EA? What is EA? It is what? FXA, and we put the value of this YA. And what is AX? That is YEA. And YEA is what? YA, and YE is what? F. So in this way we have proved that A star A is what? F. So we have proved A star is equal to E and A star A is equal to F. Now you see, as an A and A star are since A star L A star, this we know that since A dash L A dash always, so in this way A star L A dash, correct? And A star A dash is what? This is E, you know. So that is A star L E. And we know that ELB. E is in what? Where is E? E is in LB. So ELB A star LE and ELB implies that A star LB. So A star is in LB. We have, isn't it? A star is in LB. Now, since A star is equal to A star and R A star, see, we know that A dash and R A dash are always are related to each other. So A star R A dash, because A star is what? Inverse. So this is true, and this is what? F. So A star R F and F R B implies A star R B. So what we have proved, A star is an LB, A star is an RB, it implies that A star LB, A star RB in A star comma B belongs to L intersection R, so A star belongs to HB, isn't it? A star belongs to HB. So we have proved that A star is in HB and A star is equal to E and A star A is equal to F. So in this way this part is proved. So finally we will do the last part of 2.3.5. no H class contains more than one inverse of A. No H class contains more than one inverse of A. So basically what is the idea? We will take, for example, two inverses in H class, and finally we will prove that both inverses are equal to each other, isn't it? So suppose A dash and A star are the two inverses of A inside the single H class HB, correct? So it implies that idempotents A dash and A star belongs to HB. So idempotence will belongs to HB, correct? Now, as a corollary of Green's theorem, we have seen that no H class can contain more than one idempotent. So by corollary 2.2.6, we have seen that A dash is equal to A star. Similarly, just we can write like this without mentioning this. So similarly, idempotent A dash A and A star A both will be equal, isn't it? Now calculate A dash. A dash will be what? A dash A dash, or replaced by A star A into A dash. Now again replace A star A star, and now it will be what? A star. So in this way we have proved. Just write like this. So my two inverses belongs to single H class, say H. No, it belongs to H. We need not to mention. It belongs to same single class H. So in this way we have proved that and no H class contain more than one inverse of A. Correct? Now we move to the next theorem. So basically this theorem tells us to locate the inverses of the element, because in a regular semigroup element have more than one inverses, but this part guarantees us that no H class contains more than one inverse, so we can locate inverses in a D structure, correct? Now we finally move to proposition 2.3.5. This will be the last result of our lecture, last result of today's lecture. Proposition 2.3.5. This theorem was basically 2.3.4. What I have written 2.3, corrected. It was 2.3.4. Now we will do position 2.3.5. Proposition 2.3.5. We add importance in a semigroup S, then E comma F belongs to D if and only if there exists A belongs to S and an inverse A dash of A such that A dash is equal to E and A dash A is equal to F. Basically we use previous theorem to prove this proposition. Let AF be idempotent in a semigroup S, then E F belongs to D if and only if there exists A belongs to S and inverse A dash of A such that A dash is equal to E and A dash A is equal to F. So if we see the first part, for example, if we have if we have EDF, let EDF, it means what? Then EL ERA A belongs to S, correct? Then we have this. There exists some A in S, so that ERA and ALF, correct? So from here, this we get, it implies that E belongs to RA and F belongs to LA. So we have E belongs to RA intersection LE and F belongs to LA intersection RF, isn't it? Because ELE is obvious because L is green equivalence, is reflexive, so always E and E are related to each other, F and F are related to each other. So you see E belongs to R intersection LE and F belongs to L intersection RF. Now we can apply previous theorem. Previous theorem second part. What is that? That if B is in D such that if R intersection LB and LB intersection RB contains an idempotent E and F, then what happens? Then HB contains inverse A dash of A, say A dash of A, such that A dash is equal to E, A dash A is equal to F. So just we apply by theorem 2.3.5 second part, there exists A dash, correct? So we can apply there exists A dash where there exists A dash belonging to, there exists inverse A dash of A in RF intersection LE such that A dash is equal to E and A dash A is equal to F. So this is first part, half part is proved. Now converse is trivial. Converse is what? Converse that is if there exists an inverse A dash of A such that A dash is equal to E and A dash A is equal to F, then E and F are related to each other. It's obvious. You see, you put here A dash, you put E. This is equal to E, correct? And A dash A is F. A dash A is F, isn't it? So what we have ALF and ARE. What does it implies? It implies AL composition RF, that is EDF. In this way, second part is proved. So okay, so today we stop here. Thanks.